Hi, welcome to the SPDK, PMDK, and Intel vTune Profiler Virtual Forum. My name is Jim Harris. I'm one of the founders and a core maintainer for the Storage Performance Development Kit project. I'm going to give you a little bit of an overview today of the state of the SPDK project, tell you a little bit about where the community is, the technology, what are the features that we've added over the last year, and the future. Where do we see SPDK going in the future? So to start, for those that aren't familiar with SPDK and some of the history, I just want to go over a timeline of how the community got started. SPDK started at Intel as an internal project about 7 years ago. It's kind of crazy to me to think that the project has been going on for this long. About 2 years later, we started open sourcing components of SPDK out on GitHub, and the first was the NVMe driver. That's sort of the bedrock of SPDK and really what got the project started. Since then, all of the modules in SPDK are completely open source with a BSD license that you could get out on GitHub. In 2016, we released an NVMe-over-Fabrics target for RDMA. This was a big step because now we were getting out of not just the NVMe host driver, but also being able to support NVMe and target use cases. In 2016, we had the first SPDK summit in PRC. We've had annual summits in PRC since then. Normally, I wish I could have been doing this presentation in Beijing, but unfortunately, I need to do it from here in Arizona in the US this year, but I look forward to hopefully being able to do that in China in the future. While the project started just within Intel, it has quickly grown, and we have a lot of external contributors, a lot of companies that are contributing to SPDK. In 2017, we had our first core maintainer from outside of Intel, Shuhei Matsumoto from Hitachi. He continues to be a prolific contributor to SPDK and is a really critical resource for the project. And then in 2018, the NVMe working group released the NVMe TCP specification. And the same day that that was released, we had a fully functional NVMe TCP target. This was a really big step. It really showed how SPDK was really in lockstep with the emerging standards. And we continue to push features out with SPDK, with the host driver and the target to support the new features that NVMe is releasing. But then let's look a little bit at what's happened with the community over the last year. Core maintainers are a huge responsibility for the project, the roles that they play in really shepherding the project moving forward, reviewing patches, giving feedback. We were able to add 2 new maintainers this last year. Alexei Marchuk from Mellanox NVIDIA. He has been very focused on NVMe, both the target and the host side, with a specific focus on both RDMA and TCP. And then Tomek Zavadsky, who's been involved with SPDK for several years, he also came on as a core maintainer. He's been involved in a number of technical areas in SPDK, and probably one of the biggest things that he's been really owning over the last couple of years is our release process to make sure that we have good quality on-time releases of the SPDK project. Back in November, before COVID hit, we had a developer meetup that was hosted by Nutanix. This was a great session. I think we had about 15 developers there from companies like Intel, Nutanix, eBay, Fujitsu, Amazon. Had a lot of really great discussions. It's something else that we've always tried to hold annually. I look forward to when we can maybe start to do these again once the pandemic calms down. Earlier this year, we had a similar virtual forum in the U.S. based on U.S. time back in June, and so this was a 3-day forum covering SPDK, PMDK, and the Intel vTune Profiler. We had about 630 attendees over 3 days, so it was very well attended, and I look forward to seeing the attendees for today's forum as well. And then as SPDK has grown, the amount of hardware that we need to do the testing continues to grow. And Intel continues to have what I would say the primary CI that has the primary vote for patches before they can go in to the tree. But we have done a lot of work to enable additional CIs to come on board as well. So both Mellanox and Broadcom have their own CI systems with different types of hardware, with either Mellanox NICs or Broadcom FC controllers. And then they can also provide their input into the CI just to make sure that we have a very broad set of results for the patches that are going into SPDK and making sure that we don't have regressions. And then one of our biggest milestones was our first LTS release. So we had our first one in January, earlier this year. We'll be doing another one in January of 2021. And so, this is where we've heard it clearly from people who are using SPDK that they want to have a release that they can, reliably use for 1 year, maybe cases where they can't pick up the quarterly releases. And so we'll continue to do this on a yearly basis moving forward, not backporting features, but backporting critical bug fixes. So when we look at the patches, so one of the things we like to look at is on a year-by-year basis, how many patches are being contributed to SPDK, how many committers, and then also starting to look at, early on in the project, it was a very small handful of people who were doing, the bulk of the development and kind of looking at how that evolves over time. And so you can look here for the most recent. Over the last year, we just did our 20.10 release, October 31st, so this is very, very recent data. You can see the patch count, very similar to what it was the year before. The total number of committers has gone down a lot, but at 76 committers, there's still a lot of people that are contributing to SPDK across a lot of different companies. And then we're continuing to see those patches coming in less and less from those top 10 contributors and more from the other contributors. So we're seeing that the patch workload, the patch commits coming from a more broader set of committers. And we also like to look at our GitHub statistics. So really tracking how many people are downloading SPDK from GitHub, who is going out to the GitHub site to view documentation, etc. We continue to see this increase. The number of page views has been similar to the last year, but we're seeing about a 25% increase year over year on the number of different people that are coming to SPDK on a daily basis. Okay, so next, let's take a look at the technology. So what are some of the key features that we've added over the last year? So of course, SPDK started with a performance focus, and that continues to be the focus. That's why people like SPDK, why they want to use SPDK, because they want to get the best performance and the best efficiency possible. And this continues to be an area that we find more ways to improve the performance and improve the efficiency. We're up to we've been able to demonstrate over 14 million IOs per second on a single Intel Xeon core. This is huge. This is really phenomenal performance. There's a good blog post on spdk.io that Ben Walker authored that goes into a lot of the details of the things that Ben and I did to push this performance even further. And then on the NVMe over Fabrics target, specifically TCP, I think you'll hear Zhe Yang talk about this a little bit more later today. But there's been a lot of improvements on how we use the kernel TCP stack within SPDK. So SPDK, we've made a decision. We are going to be moving forward with the kernel TCP stack. We're not pursuing as a project any of the user space TCP stacks anymore, primarily because the kernel has a lot of facilities to get really outstanding performance and efficiency. The biggest one was using message zero copy for transmitting data. This is some work that Ben Walker did last year, and what it allows us to do is when we are transmitting data back to an initiator, we can tell the NIC to basically transmit the data directly out of our buffers and completely avoid the extra user to kernel data copy. And so based on this, we've been able to almost double the performance of our 4K random read high Q depth workload, up to 3.5 million IOPS on 8 Intel Xeon cores. This is huge. And this one, which I think is just as impressive, if not more, is when you're doing large sequential reads, we're getting very close to RDMA type efficiency here. So we can saturate over 14 gigabytes per second of network traffic for NVMe TCP/IO using just a single Intel Xeon core. And so this is another area we're going to be continuing to look at improvements moving forward. We think there's some potential with IOU ring to get some benefits on the RX side as well. And then logical volumes. This is a key feature in SPDK. Allows you to take NVMe storage, logically partition it, be able to present it to different NVMe clients, iSCSI clients, virtual machines using vhost. Tomek Zavodsky, our new core maintainer, he created a new metadata layout to make this much more efficient when you're using it for thin provisioning. And then we've also done some other IO path optimizations, which got us about another 10% better performance per core. So next, so Intel DSA. This DSA stands for the Data Streaming Accelerator. You'll hear the driver called ID XD. This is a accelerator that's going to be available in future Intel processors, and it effectively replaces the Intel Quick Data technology, also known as IOAT or Crystal Beach DMA. And Paul Luce has been driving the work on this. These drivers are actually upstream, even though the hardware is not broadly available yet. The SPDK drivers are there. We've been able to test them with internal emulation frameworks, so those are going to be ready once you have systems that have this DSA capability on the CPU. One of the other things that Paul worked on was we used to have a copy engine. So we had a framework where you could, if you're doing copy operations, it would do it just using memcopy, unless you had an offload engine like Crystal Beach DMA to do the data movement. But as we looked at DSA and some of the other features that it adds, we said we need this to be extended, and so it's now called our Excel framework. It supports not just copy, but also things like fill, dualcast, CRC32C operations. There's other things that this could be extended to do in the future. And it also supports operation batching, so you can do things like batch up a bunch of operations, submit them all to the hardware at once, which can also get you better efficiency. And so for all of these, we'll offload them to Intel DSA or to the IOAT engine if those are available. Otherwise, it will use the CPU to do those. And if it does use the CPU, it'll use ISA-L, which is the most efficient software algorithms to do these types of calculations. And then the next step will be integrating aspects of this into our NVMe over Fabrics and iSCSI libraries in future releases. So for example, one of the things we're going to be starting this next quarter is for NVMe using the offload to be able to do header and data digest calculations, so the CRC32C. Okay, next, SPDK top. So one of the interesting aspects of using SPDK or any pulled mode application framework is that when you have pulled mode threads, top doesn't do you a lot of good, right? It's going to show you that you have a core that is 100% utilized. And so what we found is we need to have utilities to be able to get more insight into what's happening inside of the SPDK application. And so Maciek Szwed from Intel developed this SPDK top application. It's a terminal-based UI where you can get information on a per core level. We capture busy and idle statistics, so basically you can tell how many of the CPU cycles were spent doing real work, which we would call busy work, being busy, versus idle, where it's just polling for more work to do. And then we can also break that down on an SPDK thread level or even an SPDK polar, so that you can look at the different polars you have in your application and see which ones are spending time and which ones are spending time doing real work versus being idle. This is going to be really important. I'm going to talk about this in a second, but it really gives us good development and debug tools for some of the work that we're doing around scheduling SPDK threads for power efficiency, being able to do things like, monitoring CPU frequency modulation if you're using technologies like Intel Speed Select. And so this is a tool I think is going to continue to get more work as we move forward, to really be a key in continuing to drive efficiency into SPDK. So not just the performance, but now even looking at it from a power perspective as well. So NVMe over fabrics, pluggable transports. So for a long time, SPDK, we talked about RDMA, which was developed a few years ago, and then when we added TCP, we needed to have the ability to support multiple transports. There's a lot of common code that's shared between these, and so we've developed this NVMe transport API. So on the host side, you have a common NVMe driver API. The only difference when you're connecting to a controller is the transport ID. It could either be a local PCIe SSD or it could be a remote subsystem. And so, then based on that, based on the transport of your controller, it will the operations will get dispatched to one of the transports: PCIe, RDMA, TCP. On the target side, we also have a fiber channel transport that was added in the 19.07 release last year. And then we've also added the ability to have out-of-tree custom transports. And we're going to talk a little bit more about what some of those might be. I think the key part here is that we're really looking at NVMe over fabrics and that target library to really be a common library for emulating and implementing NVMe target devices. Next, NVMe character devices. So manageability is obviously key for any storage system, and SPDK for a long time has provided a framework and utilities for managing SSDs. So we've had a tool called NVMe Identify, where you can have SSDs that are attached to UIO or VFIO, and it will issue identify commands and do a nice pretty printing of all the characteristics of the SSDs attached to your system. And then we've also had JSON RPC interfaces so that you can do things like be able to configure a target, to be able to add subsystems, to be able to attach to new SSDs. And so there's a long list of RPC interfaces that we've added over the years. But one of the pieces of feedback that we got, this was actually a big topic of discussion at the developer meetup at Nutanix last year, was using native NVMe CLI for being able to get access to information for SSDs being controlled by the SPDK driver. And so what we've done is we've taken Linux QUS, which is character device and user space. What it allows us to do is we can basically emulate a kernel character device so that NVMe CLI thinks it's just talking to a normal kernel NVMe namespace or controller, but instead all of those ioctls are being implemented in user space by SPDK. And so this is really nice. Now anybody who's already very familiar with NVMe CLI maybe has use cases where they're using the Linux kernel driver in some cases, or SPDK in others. Now they have a single NVMe CLI utility that they can use for both. And it's not just NVMe CLI, it's any utility that leverages those character devices. So things like smart control for doing smart air detection, things like that, those will work as well. Then Intel VMD. So VMD stands for Volume Management Device. This is available on root ports of Intel Xeon Scalable processors. And the feature itself enables better SSD hot swap reliability and then also LED management. So what it does is it allows a host driver to really, in all cases, be able to intercept any sort of hot plug events. So on systems where maybe the system firmware, BIOS, maybe doesn't have all the hot swap reliability that you depend on, you can have a driver that can help manage that instead. And so in some cases, using the kernel VMD driver is okay, but there's other cases where you need a native SPDK VMD driver, and so that was added in the 19.07 release last year. And so then what this means is you can actually have SPDK own the VMD device, and this driver will actually enumerate all of the NVMe SSDs that are behind it, and then you can just use the standard the standard SPDK NVMe driver with those SSDs. Okay, and then finally, power efficiency. So I touched on this a little bit earlier. In this last release, Maciek Szwed, this was another thing that he worked extensively on with Ben Walker and myself, is a scheduler framework for these SPDK threads. So in SPDK, we have a bunch of SPDK threads that the different modules and libraries will create. And what we want to be able to do is, based on heuristics for how busy or how idle those threads are, we want to move them between CPU cores. And then in some cases, if the system is relatively idle, we can even move SPDK threads completely off of all the cores except for one and put those other cores then to sleep. And so this allows us to drive more power efficiency into these pulled mode type applications. But it's not just the scheduler. We also added a framework for CPU frequency governors so that we can implement governors for technologies like Intel Speed Select. And so then this is cases where maybe you've moved a certain amount of work onto a core, but you detect that it's still not that core is not 100% utilized. You can dial the CPU frequency down and achieve additional power savings. And then the other thing that we've actually been working on, Xiaodong Liu has been working on this, and he's going to be talking about this more later today, is what we call interrupt support. So this sounds counterintuitive. SPDK is all around pulled mode software, but there are actually cases where the advantages of doing user space development, leveraging libraries that have already been developed in SPDK, but maybe you have a lower performance requirement, and you're in a situation where dedicating a single core for the application isn't feasible. So for example, maybe you need to run a whole bunch of SPDK applications, one for each container. Well, now we've started to add support for those types of use cases. And then let's look a little bit at the future. So where is SPDK heading? What are some of the things that you might expect to be able to see us talking a lot more about over the next year or so? So I talked a little bit about the pluggable transports for NVMe over fabrics, and this has gradually evolved over time, and as I mentioned, we have a lot of very common code for general NVMe target functionality. And so we're finding a lot more cases where you want to emulate an NVMe controller, not just as a network fabrics target with like TCP or RDMA or fiber channel, but now looking at things like for virtualization. So there's an initiative going on right now with Red Hat and Nutanix and Intel and the QEMU community around VFIO user. And what this allows you to do is to fully implement a PCIe device in user space, emulate that PCIe device. And the primary use case right now for this would be to fully emulate an NVMe SSD. And so what this VFIO user transport would allow us to do is use all that existing SPDK NVMe target library functionality and just develop a VFIO user transport, and now we can emulate NVMe SSDs to a virtual machine using the standard inbox drivers for those VMs. And so this is a really exciting use case, and I think you can expect to see a lot more progress over this in the next 3 to 6 months. The specification for this within the QEMU community is very close to being finalized. And then also SmartNIC. So there's SmartNIC use cases where you're presenting NVMe interfaces to a host, and again, you want to run SPDK software on that SmartNIC. And so this is another great use case for this pluggable transport framework, to be able to develop transports that are specific for that SmartNIC so that you can run that SPDK software on that SoC. So next, computational storage. I think the idea here is it's been around for a very, very long time. It's just the use case of moving the compute closer to the storage. And as data analytics just explodes, this is really becoming more and more important in the data center. And so, SPDK, myself, Ben Walker, have been involved in some ongoing efforts that have started in NVMe around standardizing this. And, we really see this as not just fixed function, doing things like compression, hashing, erasure coding, but also programmable function. So being able to actually ship code in some format to another device and then be able to operate on blocks that are read on the device. And so you can avoid some of that back and forth across the host interface or across the network interface. And I think the key part here from an SPDK perspective is you can really expect SPDK to be at the center of these efforts. So as NVMe moves forward and NVMe maybe gets some things standardized, you can expect to see SPDK implementations of this in the future. And then, of course, more performance, more efficiency, more scalability. So for NVMe over Fabrics, a big focus over the next 3 to 6 months is going to be scaling this to thousands of connections and thousands of namespaces. So, we've done a lot of testing, but with a more limited scaling factor. So there's been some people in the community, companies like HPE, who've been doing a lot of active testing and have found some scalability things that we're actively working on. Dynamic thread scheduler. So this is taking the framework that that we've built, that we talked about earlier, where we actually have a scheduler that you can enable with SPDK to dynamically move these threads between cores. Dynamically move the frequency up and down if you have Intel Speed Select technology on your CPU. And so that's going to be another major area of focus, is to have that entry for people to start using, to start testing, for us to continue to evolve the power efficiency aspects of SPDK. And then finally, from a data protection standpoint, so continuing to look at how to make diff and dix more efficient within SPDK. So we're doing performance measurements there, looking, are there additional optimizations we can make? And then, as I mentioned, looking at things like header and data digest with NVMe and iSCSI. How do we leverage offloads that are available in things like Crystal Beach DMA or upcoming DSA to be able to accelerate some of those calculations? So that brings me to the end of my presentation. Thank you for listening. Really encourage you to attend the SPDK and the PMDK and the Intel vTune talks today. I think you're going to hear a lot of really good presentations from a lot of experts in these projects and from companies who are actively using these projects. And so I think if you're getting up to speed and you're wanting to learn more about these, it's a great opportunity to do that today. If you're interested in SPDK, keep up to date on what's happening. We have a blog where we post updates, things that are happening within SPDK, our releases. We also have very extensive performance reports. If you go out to spdk.io, we have a team that publishes quarterly reports. So how does NVMe TCP perform as you add more cores to the system? How does it perform when you're doing NVMe IO and doing comparisons between using SPDK and Linux AIO and IOU ring? A lot of great information. If you're really interested in digging in more to those performance details, check out those performance reports. And of course, jump in. We really welcome new contributors. We have a very active Slack community, so you can get on channels there if you've got questions, you want to contribute, you're looking for areas to contribute. Please jump on there. There's a lot of people on there. We have people across the globe working in SPDK. There's always going to be somebody around to help answer questions. We've got our mailing list, and we have our bi-weekly community meetings. So for Asia, we actually have ones on, I guess it would be around Thursday at noon, where you can call in, and we have people from the SPDK community that discuss, open topics, go over bugs, debug things. It's another great way to get to meet people within SPDK. So thank you very much. Hope you enjoy the rest of today's talks.